In section 3.2, we examine two important theorems about derivatives. The first one is called Rolle's theorem, and the second one is called mean value theorem, and they're very closely related. So let's start by looking at Rolle's theorem. Rolle's theorem has three conditions. It says if we are given a function, f, and f is continuous on this closed interval from a to b, and f is also differentiable on the open interval from a to b, and finally that f of a equals f of b. If all three of those conditions are met, then there has to be at least one number c in that interval from a to b such that f prime of c equals 0. Now, there could be more than one point, but there has to be at least one point if these conditions are met, at least one point where we get a horizontal tangent line, just like we do here, where x equals c. Now, there are obviously cases where Rolle's theorem will not apply because the three conditions are not met. So let's look at some of those. If we look at the picture on the top left in this slide, we'll see that that function has a point where the function is not differentiable. It has a cusp on the graph, and since the cusp is there, the function is not differentiable, and we're not guaranteed any point where the derivative is equal to 0. Now, let me point out that there could be a point where the derivative is 0. There's not in this case, but all we know is that Rolle's theorem does not guarantee us that there is a point where the derivative is equal to 0. In the picture at the right, top right, you see another graph where one of the conditions is not met. Technically, two of the conditions are not met because in this case, since f is not continuous, it cannot be differentiable, so it is actually neither continuous nor differentiable on the interval that we're given. And since that is true, you can see that we're not guaranteed a point where the derivative would be equal to 0. And finally, we can look at the bottom middle graph, and we have an example where f of a is not equal to f of b. And if that's the case, then once again, we're not guaranteed that there's a place where the derivative is equal to 0. But if all three of those conditions were met, we would be guaranteed that point. Now let's look at the mean value theorem. The mean value theorem starts out with two of the same three conditions. It starts out with f being continuous on the closed interval from a to b and differentiable on the open interval from a to b, but it removes the requirement that f of b has to be equal to f of a. Okay, so there are only two conditions for this theorem, and in this theorem, if those two conditions are met, then we know that there has to be at least one number c in the interval from a to b, such that f prime of c equals f of b minus f of a over b minus a. Now that f of b minus f of a over b minus a should look very familiar, and so let's restate this in ways that we've already seen that f of b minus f of a over b minus a. So one way we could say this is to say that if we have an interval where the conditions are met, continuity and differentiability, if those conditions are met, then there has to be at least one point on the interval where the tangent line is parallel to the secant line that passes through the endpoints. So you see here we have the secant line passing through the two endpoints, and we have a parallel line passing through this point right here. Okay. Another way of restating that, one more time, would be to say that when the conditions are met, there must be at least one point on that interval where the instantaneous rate of change, f prime of c, is equal to the average rate of change, f of b minus f of a over b minus a. Just three ways of stating the same theorem. One of them is very mathematical. The others are more interpreting what's going on in that case. Now, let's see a problem in which we could make use of the mean value theorem. So we're still looking at the same graph, but we're told that the function here is 4x minus x squared. We would be given this information that's in yellow here, the function definition and the interval on which we are looking at the function, which is the interval from 0 to 3. So we start by checking our conditions. Is the function continuous on the closed interval from 0 to 3? Well, this is a polynomial function. We know that it's continuous everywhere. So that's good. It's continuous from 0 to 3. Is the function differentiable from 0 to 3? Once again, it's a polynomial function, so we know that it's a differentiable everywhere, which includes, of course, the open interval from 0 to 3. So since we have a continuous and a differentiable function, those are the only two conditions we have to meet to apply the mean value theorem, then we know that there has to be a point at which the slope of the tangent line is equal to the slope of the line passing through the two endpoints. So we want to find all the points where that happens. In this case, we can see there's only one. And so to do that, we need to know what that slope of that secant line is. So we say f of b minus f of a over b minus a, which we can see pretty easily. That secant line is just the line y equals x, because it passes through the points 0, 0 and 3, 3. We should recognize that as the point y equals x, but we can also easily find that the slope is 1. Now that we know what slope we're looking for, we need to take the derivative. Pretty easy derivative to take. F prime of x equals 4 minus 2x. We take that derivative and we set it equal to 1 because that's the slope we're looking for. So 4 minus 2x equals 1. If we solve that equation, we find that the point we are looking for occurs when x equals 3 halves. And I will do a little erasing there because I accidentally marked out the next line a little bit. Once I know the x value, all I have to do is plug it into the original function. One more time, always remember to plug into the correct function. Don't plug this into the derivative, plug it back into the original function. When I plug 3 halves into the original function, the function value I find to be 15 over 4. And so the point where the tangent line has the same slope as the secant line is this point 3 halves, comma 15 fourths.